Buenas tardes, mi nombre es Catalina Tamburrino y soy estudiante de la carrera de Medicina en la Universidad Católica del Norte. En nombre de Fundación Puerto de Ideas y Expandida BHP, quiero darles la más cordial bienvenida a la siguiente actividad del Festival de Ciencia Puerto de Ideas Antofagasta 2021, la conferencia Bigbang, el origen del universo. Nos acompañará Neil Turok, físico teórico sudafricano, quien nos intentará explicar qué hubo antes del Big Bang utilizando las teorías de la física. Explorará la idea de que el Big Bang fue en realidad una transición desde una era de contracción a nuestra era actual de expansión, un punto de quiebre cuántico en un universo que ha existido siempre y que continuará expandiéndose infinitamente. Esperamos que disfruten de la actividad.
Okay, thank you very much for that kind introduction. It's my privilege to join you today to tell you about some very ambitious and exciting science to do with the Big Bang, which is, in my view, the greatest puzzle in all of science. Where did everything come from? So I'm going to begin by setting the scene. I know Chile is a very beautiful country, and you probably have scenes like that where you are, with a cozy house in which we live. It kind of represents the earth. And then when we look up at the sky, we see these magnificent things, the beauty, the size, the scale of the universe. It's kind of overwhelming. But the amazing thing we've learned in science is that it is comprehensible, at least at some level. We can use mathematics and experiments we can do on Earth and now in space to determine the laws of nature. And they seem to apply everywhere with incredible accuracy. So the biggest puzzle in science is to figure out, where did all this come from? So the story really begins in Africa, where our ancestors discovered mathematics over 20,000 years ago. And this is the oldest artifact in the world that involves numbers and counting. And we still don't really know what it means. What's pictured is two sides of a bone. And on that bone, you see the marks. And the marks are arranged in groups of prime numbers, all the prime numbers less than 20. And so we don't know what they were doing or what they were counting or what they were reasoning. But in the middle of Africa, and this is its location, right in the center of Africa, in the Congo, next to Uganda, in the middle of Africa, somebody was using numbers to quantify the world. And this is where we are today. This is our modern understanding of the universe around us. At the center of the picture, you see the solar system, the sun and the planets revolving around it. And then as you go outward into space, you encounter galaxies, these dots, stars are dots, and the galaxies are the whirlpools of stars, collections of stars. And then as we look outwards further and further, we are seeing the universe as it was earlier and earlier, because light travels at a finite speed. And so when we look at very distant objects, we're seeing them as they were a long time ago. So at the far reaches of what we can see, we see the universe emerging, almost the birth of everything, and we can really look at it. And you see these cobwebs at the edge of the picture. This is really showing you how matter clumped into galaxies. And I'll show you some pictures later of the sky, which reveals this, the beginnings of this clumping process. And then as we go back further, we see the red circle. And the red circle is really where light was released from the dense matter of the early universe. And since then, it has traveled through space to us. And if we go out even further, we see the gray circle, the outer boundary. And that gray outer boundary is the most paradoxical thing of all. It's the Big Bang. Now, it's strange in this picture that it surrounds us, the Big Bang, but actually it's the tiniest thing we know of. And the reason for that is that space expands. It's not standing still. And so as we look outwards, the size in this picture is a bit misleading because actually the outer parts of the diagram have shrunk as we go backwards in time. They shrink, they get smaller and smaller. So the very edge of this diagram is actually a point. And I will show you that in a moment. Now, observations in the last decades have shown us incredible things. And I want to show you one of the most incredible, which is two neutron stars, very dense objects, essentially large atomic nuclei, several kilometers across. And they orbit each other and spiral inwards. And I'm going to just stop the movie there. They orbit each other and spiral inwards, and then and eventually collide. So they spiral in, and let's just watch them collide. Okay, they come closer and closer. And when these two essentially very large atomic nuclei, when they collide with each other, they release energy. It's essentially nuclear energy. It's the same energy as in the nuclear bomb. And so there's incredible amounts of radiation which are released as these two atomic nuclei merge. And the way in which this event was seen is itself very remarkable, because in the first phases of this orbiting, you see they're not touching, they're spiraling inwards. If I play the movie, you'll see waves beginning to go out. Now, initially it's gravitational waves, and then it was radio waves, and finally it was X-rays and gamma rays, very high energy radiation. So this event was seen a couple of years ago, and right now radio telescopes like this one, and there are similar radio telescopes in Chile, are allowing us to see the whole sky. Here's a picture of the sky with these objects going off, flashing. These are called fast radio bursts. And because the whole universe is flashing signals at us, we can use that to understand what's going on in the universe. And so our knowledge is growing exponentially of exactly how the universe works. I should mention just a little bit about that telescope I showed you. Why did I show that one? The most interesting thing about this telescope, it's what's called a software telescope, meaning it's rather a cheap array of radio detectors. This is not the most expensive part of the telescope, these wires and collecting the collecting area for radio waves. The expensive part is in the little hut on the left down there, and that's a supercomputer. And the supercomputer is actually focusing the telescope in software, in other words, in the computer. And the wonderful thing about that is that you can focus this telescope in principle on every point on the sky at the same time, because you focus using essentially computer algorithms rather than mechanical collecting dish. So this is a new generation of radio telescope, and it's allowing us to observe in real time the whole sky in principle. And so that's really exciting. In the next decade or so, we're going to see incredibly powerful new radio telescopes combined with computer processes, fast computer processes, to allow us to observe the whole universe all the time. Now, why is that so interesting? You see, when these two neutron stars merged, as I said, it's like nuclear fusion, the fusion of two atomic nuclei. and it releases a huge amount of energy, and the energy blasts pieces of those large atomic nuclei into space. And what are those pieces? Well, the pieces are just the nuclei of atoms. And so here is the periodic table of elements, which I'm sure you all saw in chemistry at school. And if you look at the heavy elements, which are the ones in the lower part of the table, the proportion of them shaded orange indicates the fraction of those elements which were formed in merging neutron stars, just like I showed you. So when we look at platinum or gold or uranium or palladium, these were mostly formed in events like the one I showed you. And the way we detected that event was incredible. We detected it first in gravitational waves, emitted because the two bodies were orbiting each other, emitting disturbances in space-time. Secondly, we saw radio waves detected in that telescope like the one I showed you. And third, we saw X-rays, all combined. And so we literally saw the process in which the heavy elements in the universe were created. And if you think about the amount of gold, for example, created in that event, it's really astronomical. It's tens of planet Earths of pure gold, which were created in an event like that. So that's what we're now able to see in the universe around us. It's really remarkable. Well, what is the world made of? What is the universe made of? First of all, they're atoms, like the stuff we are all made of, and their constituents, the atomic nuclei and the electrons which orbit atomic nuclei in atoms. And of course, atoms combine to form molecules, and molecules make up all the stuff we see around us. But as well as that, we have light, which is a very magical substance. It, of course, travels at incredible speed, the speed of light, and we use it to see things and to communicate with each other. For example, in cell phone communication and so on. These forms of radiation I've mentioned, the X-rays, the gamma rays, the radio waves, the light, these are all the different forms of the same thing, electromagnetic radiation, or we can call it light for short. In addition to that, we have gravity, which of course holds us on Earth, and it also governs the clumping of matter that led to the formation of galaxies and stars. And it also governs the expansion of the universe, the fact the universe is growing in size with time. And in addition to this, there are two more mysterious things which are still a puzzle. But I'm going to tell you that one of those two puzzles may be solved. And the other one may be so simple in a sense that it may be sort of the essence of the universe, the true essence of everything. So let's deal with the first one. This is a famous puzzle in cosmology, the puzzle of the dark matter. And this is my favorite picture, which illustrates the dark matter. Now, as I've mentioned, most of the stuff around us in our vicinity is made of ordinary matter, atoms. But we see from looking out at the universe that there's another form of matter that also clumps around ordinary matter. So in particular, in this picture, the blobs, the light blobs in this picture are actually galaxies. So each one has 100 billion stars. And these galaxies attract each other under gravity, and so they form clumps. So galaxies are themselves clumped into what is called clusters of galaxies. Now, how do we examine a cluster of galaxies? Well, we are able to see things in the cluster even when those things are invisible. And the way we see them is firstly by looking at different wavelengths. So if we can't see it in light, we might look in radio or in X-rays. And in fact, the red color in this, so the white color shows galaxies seen in ordinary light. The red color shows the gas, that's hydrogen gas, as seen in X-rays. And you see a strange feature here, which is a sort of triangular front, which might be puzzling. And then, so that's what the gas is looking like, the hot gas in the cluster. And then there's the blue shading. Now the blue shading shows us what the dark matter, how it looks. And how do we see the dark matter? It's dark, so we can't see it. So how did they make this picture? Well, the way they made the picture is the same way that you can see a glass of water on the table. Now, water is transparent, so we can't see it. But we have no problem seeing it, and the way we see it is because the water bends the light. So if you look at something behind a glass of water, or a drop of water, you will see it distorted as the light passing through the water, entering the water from the air is bent, and then it's bent again as it re-enters the air from the water. So gravity clumps the dark matter in turn bends the light. And from that bending of the light by the dark matter in this cluster of galaxies, what that means is just the distortion of background images. From that distortions, we can infer the distribution of the dark matter. And as you'll see, there are two lumps of dark matter. One is here and one is there. And then we have this gas. Now, what is this picture? What does this picture represent? Well, I think there's a clear interpretation. You see, these dark matter lumps move around through the universe because they're clumping under gravity. They're drawn to each other by gravity, and then they orbit each other, and they can collide with each other and move through each other. So imagine that this clump actually moved through that clump, and that clump had a bunch of gas collected within it. Well, as this one moved through, it would drag some of the gas through its gravity. It would drag some of the gas out and force it through the other gas to make this sort of shock wave, heating up and pulling over the remaining gas, as is here, and move along. And so this is the interpretation of this picture, is two dark matter clumps collided, one passed through the other and dragged this gas behind it. And so one can do computer calculations and simulations which verify that this is very probably what happened. And when you do it, you see very directly that the way in which ordinary gas, made of hydrogen mainly, and dark matter, the way they behave is quite different. The dark matter doesn't heat up. It just clumps under gravity, but it doesn't interact with other matter at all, except through gravity. So there seems to be this other kind of matter in the universe, which is dark. It bends light under gravity. It attracts itself under gravity, but we can't see it, not in a straightforward way anyway. Now, at the end of this lecture, actually, I'm going to explain what this dark matter is based on what I claim is the simplest idea we now have, which does not involve any new physics beyond the physics we already are quite confident about. But that'll come later. Let me move on to the second mysterious component called dark energy. Now, what is dark energy? So I showed you a very beautiful picture made by a very expensive telescope, and so of the dark matter. What am I going to do for dark energy? And the best I can do is show you this picture of it. which of course was made by a very cheap telescope on my laptop. But that is what we expect it to look like. Dark energy is completely uniform and dark. It doesn't clump. It doesn't change. In fact, it's the most simple form of energy you could possibly imagine. So, and Einstein even postulated this form of energy in 1917, a long time ago. Now, what is special about dark energy? It's the most symmetrical form of energy. It looks the same. If you move through it in space, it's not lumpy. It's completely uniform in space or even time. If I sit at a given point in space and wait, the dark energy will always be exactly the same. Its density does not change as the universe expands. Even if I move through the dark energy, it doesn't, or it moves relative to me, I see no difference at all. This is very strange. You know, with ordinary matter, if you move very fast, or if it moves very fast with respect to you, we say it has kinetic energy. I mean, it's quite different. It's in motion. With dark energy, uniform motion is meaningless. It's just the same, and no matter how we move. If we're moving uniformly, we don't see any change in the dark energy. And then its most bizarre property is it repels under gravity. It doesn't even attract like other matter does. It causes the universe to expand faster and faster, or accelerate the expansion. So those are the two strange forms of energy which we need to describe the universe around us. Ordinary matter comprises about 5% of the total energy in the universe, the dark matter about 25%, and the dark energy about 70%. And because everything else gets diluted as the universe expands, but the dark energy doesn't, the dark energy will dominate the future. It will, in billions of years in the future, the dark energy will be the dominant form of energy in the universe by a huge amount. So that's it. So and then the amazing thing about the universe is that on large scales, very, very large scales, the universe we see is astonishingly simple, meaning we can describe it with very few assumptions, very few equations, and very few parameters. So here is a picture of the real universe on very large scales, and this was made by a satellite called the Planck satellite, looking out across the sky. And what it's picturing is the temperature of the universe on the inside of that sphere which surrounds us, which I showed in the previous slide, the red sphere. When we are sitting in the middle and we look out, this is what we see on the surface of that sphere. It's almost uniform, but not quite. These temperature deviations are, so the temperature is about 3 degrees above absolute zero when the radiation reaches us. But it deviates by about 1 part in 10,000 across the sky. And so the temperature of the sky is almost uniform, but slightly varying across the sky. Sorry, 1 part in 100,000. These variations are about 1 part in 100,000 across the sky. So we look out, we see this pattern which surrounds us. The first feature of the pattern is that the temperature is amazingly uniform, almost constant at 3 degrees Kelvin all over the sky. And then we see these tiny variations. So how do we explain this? It's very puzzling because it appears this Big Bang happened perfectly symmetrically, almost perfectly symmetrically, but also almost exactly at the same time in places that were separated by further than the light travel distance. Because if I look at 2 points on the sky opposite to each other, clearly light has never communicated between them in the past, and yet they're at nearly the same temperature. So that's very puzzling. Now, if we make a picture of the history of the universe, this is what we believe that happened in the past. Initially, at a tiny fraction of a second, there was a tiny ball of light, just a few millimeters across, from which everything we see today emerged. As the universe expanded, it cooled, the atomic nuclei formed, the atoms formed. This is the red shell of light, the inside of which the previous picture showed you. And then as the universe expands further, the galaxies form and clump. And then late on in the universe, around 9 billion years, the expansion of the universe speeds up. Why is that? Well, it's because of the acceleration due to the dark energy. The dark energy is repulsive under gravity. It causes the expansion to speed up. And here we are today, 14 billion years after the Big Bang, going into the phase where dark energy will dominate. Now, the real puzzle, which I'm going to talk about for the rest of this lecture, is the Big Bang itself. What happened there? How on earth did everything we see emerge from this tiny ball of light? And where did the ball of light come from? Well, the first thing to say is that, amazingly, the universe is somehow designed in such a way that we can understand it. And true understanding comes from combining theoretical work and ideas with observations. And amazingly, the more we think about the universe, the more we figure out how to make those observations, to see things going right back to the Big Bang itself. So this is the part of the universe we can see. And I draw it like this because imagine we're sitting here at the tip of this green shape. Now, as we follow light backwards in time, time is vertical here, going upwards. As I trace a ray of light which arrives at me, consider a ray of light which arrives at my eye today or at my telescope today. This is its trajectory. As we go back in time, the ray of light was traveling outwards away from us. But then, as I mentioned before, the universe is actually shrinking as we go backwards in time. So the ray of light will also shrink, or these two rays will approach each other, and everything will eventually collide with this Big Bang. The gray circle I showed you in that early picture is at this point. It's all been shrunk down to this tiny ball of light. So the previous picture I showed you, this one, shows you the universe when the first atoms form. Now, before this point, the universe was very dense. And it was so dense that it's opaque to light. We can't use light or radio waves to see through it. So how do we look at what happened inside the universe before this time? And the answer is nature has provided us with a way to do that. And they're called gravitational waves. They've recently been detected. That's in fact how we saw the two neutron stars coming in towards each other. The gravitational waves were detected. So we can now detect gravitational waves. And because gravitational waves travel freely through even very dense substances like this plasma in the hot Big Bang, we can use these gravitational waves to literally look at the Big Bang itself, the initial formation of the universe. So all the theories I'm going to tell you about are actually testable, even though they speak about events which happened 10 to the minus 43 seconds after the beginning of the universe, or even before. That's why the science is so fascinating. Now, where are we in all of this? And I just wanted to share with you a kind of amazing coincidence, if you like. We haven't explained this yet, but we sit in the middle, and we are very complicated beings. living beings, conscious beings, able to make decisions sometimes. And so we are very complex things. But I've told you the universe is extremely simple on large scales and rather easy to understand and rather easy to predict. Well, likewise, on small scales, things become simple. We have elementary particles and atoms and structures where we can do calculations and make very precise predictions about the behavior of tiny particles from which the universe is made. So there's a wonderful coincidence, which is if you ask, what is the largest scale which we could possibly see ever, right, in this picture of the universe I've shown you? And equally, what is the smallest scale which we could ever possibly see? One of them, the dark energy scale, is about 10 to the power 27 meters. The other is called the Planck scale. It's 10 to the minus 35 meters. And both of those scales are actually determined by gravity. The dark energy scale is determined by the expansion of the universe. The universe is expanding so fast that the distant material is traveling away from us faster than light. And so we can never see it, and we will never see it as long as the dark energy is there. So gravity, the repulsive gravity of dark energy, renders the outside of this region invisible. There's a converse effect, which is on small scales. If I try to see anything smaller than this scale, it's a very small scale, I would have to use light of the same wavelength to see it. Otherwise, my microscope couldn't focus. So I'd have to build a microscope with light of a wavelength 10 to the minus 35 meters. Now, if I did that, the photons of that light, the particles of that light, turn out to be extremely energetic. They're like X-rays or gamma rays, but much more so. And they're so energetic, they have a huge gravity, they have a huge mass, huge gravity. If you shine that light on any substance, the gravity of the light will cause the thing you are looking at to collapse and form a black hole, and you won't be able to see it. So gravity sets this limit on small scales. And as I said, it also sets a limit on large scales. Where are we? It turns out we are, in a sense, exactly in the middle between these scales. If I take the two lengths here, you see, you might say I should average them to find out the length in the middle, but that's not so interesting because one is really very small and the other is extremely large, and the average would just be extremely large. But I can do something else. I can multiply them and take the square root. That also gives me a length, and that's about the size of a living cell. So we are, in fact, life is in the middle between these two extremes. The way the universe appears, the extremes are very simple, but the middle is very complicated or messy. And viewed this way, you know, we are the messy objects in the universe, but we are, in a sense, the leading edge of the complexity in the universe. Now, what is the most popular picture of the Big Bang? Let's go back to this Big Bang, this crazy event which started everything. And I have to first tell you about the most popular picture, which is the theory of inflation. And it's a funny name because inflation is normally a bad thing in money markets or in the economy. Inflation is certainly a bad thing. The cost of things can grow exponentially. And that's where the name came from. And this idea was invented around 1980 by various people. And the idea said, well, how do you get a very dense universe, very small, very dense universe, which is expanding at this incredible rate? It's expanding so fast that it will overcome gravity and end up as large as the universe we see. So intuitively, people wanted an explosion. They wanted to say, how can I get a really big bang at the Big Bang? And I've already given you a clue how to do it, which is that the dark energy has repulsive gravity. So what you have to propose is that there is much more dark energy, not the one we see today. That's rather feeble. It's very low density. What you need is a form of dark energy which has extremely high energy density, so an extreme form of dark energy, and then you want it to decay into ordinary matter, so because we don't see it today. So it's like dynamite. You put it in, it repels the universe, and then it decays. And so literally it provides the bang. Now, a beautiful feature, so you might say this is a very ad hoc model. It doesn't really solve anything because you just put this in at the beginning. You know, that's what you did. Okay. And this is basically why I find it very unconvincing. But the idea has had some big successes, one of which was to explain these small variations in the temperature which we see around us. You know, one way to explain this is to imagine I have a form of energy, let's say like an unstable atomic nucleus, which is going to decay. So let's say a bar of uranium, unstable uranium, and the bar is going to decay. Well, different points in the bar will decay at different times. And if this whole thing is expanding, that will mean the density will get diluted more or less depending on the time at which you converted this dark energy into ordinary energy, ordinary forms of energy. So in this way, in fact, the inflation picture did allow you to explain this pattern that we see in the sky. It's a very beautiful explanation because it involves the quantum mechanical decay of this postulated form of dark energy. And by the way, I should say, this is not just a messy picture. You know, the first time you see this picture, you might say, oh, well, that's like the pattern I see, you know, in my teacup when the tea leaves are left. It's just some random pattern. But it turns out we can predict the features of this pattern very precisely, even though the precise pattern is statistical in nature. We can't say exactly where it will be hot or cold. We can predict the properties of the pattern, which we call the spectrum. So how many hotspots of a given size are there? How many cold spots of a given size? We can predict incredibly precisely. And so these are some calculations I did in 1994 of what is called a polarization pattern of the sky. The red curve was our predictions based on observations of the temperature of the sky. So these are two different properties of the sky. One is that it can be hot or cold. The other is that if you look using polarized detectors, like polarized lenses in sunglasses, if you use polarized detectors, you can measure the polarization. And so using the temperature data, we could fit all the parameters in the cosmology. And then this is an absolute prediction, this red curve. There's nothing you can adjust. And you see the data fits perfectly. So it's quite amazing that the universe fits this theoretical framework to extraordinary accuracy. You could never do this in the lab. The real systems are more complicated. In the messy middle, it's more complicated. On the very large scale universe, on very large scales, the universe is amazingly predictable. So, and the fundamentals of these fluctuations are quantum. That's what kind of is a wonderful feature. What does that mean? Well, in quantum, I'll just show this picture of the famous double slit experiment where you send light through slits. And so the light travels as waves, but it arrives as particles. There are flashes of light. Those are the photons as the light arrives at the screen. And their location is random. But the pattern is determined by these waves. And we believe this is the same phenomenon we're seeing on very large scales in the universe. It's a quantum phenomenon. Quantum physics underlies the statistical character of the distribution. Now, some of us are not convinced by this story just because of this reason, that this is a model. It has lots of assumptions, lots of parameters, and it's fundamentally ad hoc. Nor does it explain the really basic questions like, where did all this come from? You just threw in an extra form of energy, but you didn't explain where that came from. But, you know, observations are always much better than theoretical arguments. And it turns out that this inflationary model produces these fluctuations very nicely, the density fluctuations we see, but it also produces gravitational waves. Literally, when you have this explosion in the beginning of the universe, it causes gravitational waves like echoes to be created, like echoes. They're actually produced quantum mechanically. And these are sort of echoes of the Big Bang. And they should be there, but the observations don't see them. So this is a kind of messy graph, but the vertical axis shows the strength of these gravitational waves, and the horizontal scale shows a parameter in this inflation model. The most plausible models, inflation models, are up here, and as you can see, they're steadily being ruled out by the observations, which are the blue circles. And so as the observations improve and they don't see the signal of inflation, it means this theory is more and more under pressure. You might notice there is a model which is consistent with the data, but this model, unfortunately, is mathematically inconsistent. So the only version of inflation which fits is one that just isn't allowed by mathematics. So that's not a healthy situation. Could there be a simpler and more complete explanation? So in the last few minutes of the talk, that's what I'm going to describe. What motivates me is the following philosophy, that Georges Lemaitre was actually the person who first came up with the Big Bang scenario. Strangely enough, he was a Catholic priest who happened to be very good at mathematics, and he managed to solve Einstein's equations and found that they described a hot Big Bang. And he said that progress is the discovery of a more and more comprehensive simplicity. This is another hero of mine. His name is John Wheeler. And he has this lovely saying, behind it all is surely an idea so simple, so beautiful, that when we grasp it in a decade, a century, or a millennium, we will all say to each other, how could it have been otherwise? How could we have been so stupid? So this really resonates with me. I was very fortunate to know John Wheeler when I was a professor at Princeton, and had the privilege of some nice conversations with him. And this is what my research is focused on. Now, I have to mention that I came to Chile 2 years ago at the invitation of Chile's most famous theoretical physicist. He's in the middle of the picture. His name is Claudio Bunster. Formerly, it was Teitelbaum. And we became very good friends due to his work on what I'm about to describe. And he was a student of John Wheeler. And here they are at Princeton. This is Jim Peebles, who recently won the Nobel Prize for the basic theoretical framework of the hot Big Bang cosmology and much of what I've said so far. So Claudio Bunster lives in Valdivia, and I came to meet him 2 years ago. He worked on this with John Wheeler. So it's a very theoretical framework. It's trying to connect quantum mechanics to gravity. If you want to describe the quantum beginning of the universe, that is what you have to do. You have to describe how space and time fluctuate quantum mechanically. And so I won't go into the details of this, but this theory, a very formal mathematical theory, was developed by Claudio and John Wheeler, and this is what we have used. Now, we want to describe the beginning of the universe, but in order not to go wrong, it's often a good idea to pick a more elementary phenomenon where you can gain some intuition. And the particular elementary phenomenon, which I would like to base my intuition on, is the creation of a particle. Instead of a universe, let's talk about just a particle. That's much less ambitious. And then if we're right, the way in which a particle is created is very similar to the way in which the whole universe was created. So I need to tell you about the theory of particle creation, which was developed by this person, Ernst Stuckelberg, in 1941. And I'm going to describe it with diagrams. Those of you who have studied relativity may understand these diagrams better. The diagrams show space, horizontal, and time, vertical. And so you're supposed to imagine that a particle travels through space-time. You see, this line is the trajectory of a particle in space-time. At a given time, I tell you where the particle is. So normal particles go forwards in time, and they move around in space, and so they follow some kind of curve in space-time, but they can never go faster than the speed of light. And so they're always confined to keep going forwards in this diagram or upwards in this diagram. They can never go at a greater tilt than 45 degrees in this picture, which would be the speed of light. So they're forced to keep going forward. What Stuckelberg realized is that in quantum mechanics, it is impossible to stop particles going faster than the speed of light for a short moment. And if they do that, they can even turn around and start going backwards in time, okay? Which is a very puzzling event. You have a particle going forwards, and then it turned around and went backwards. Now, from the point of view of somebody outside, they would say that at this time, there are two particles. Of course, one is really going forwards and one is going backwards, but we see both of them at the same time. And so from this outside point of view, they would say, no, we had two particles here. They're slightly different. And when they come together, they annihilate. Those two particles annihilate. And so Stuckelberg realized that electrons must be able to annihilate with their antiparticles, which are exactly these guys. And so at later times, there would be no particles. And conversely, if you have no particles, you could have two particles created. And one way of looking at it is that a particle comes from the far future, turns around and goes back to the future. And the other way is from the outside point of view, you would say, I had no particles, and then I had two. This would be the electron, this would be the positron. And so this effect is actually seen in laboratories, the creation of particles in strong electric fields. And as I've emphasized, there's sort of two points of view. One is internal. You can think about the particle living in a tiny universe where it doesn't have any spatial extent. It only has time. And as it follows its own time forward, it would see it goes through some strange period where it's actually violating the laws of special relativity. It's moving faster than the speed of light, but only for a moment, and that's allowed quantum mechanically. So it goes through this funny phase, quantum phase, and then it goes forward. And then it keeps going forward in its own time, but from the outside point of view, it's now going forward in the outside time. Now, of course, the analogy we're drawing is with the four-dimensional universe, not a one-dimensional universe. But this is the picture we've come up with, which seems to make sense, which is literally, I take this picture, replace the particle with an extended region of space, like a patch of the universe. I follow that patch backwards in time on this curve, go through a strange quantum region, and come out on the other side with that patch going forwards in time. Now, it turns out backwards in time and forwards in time, when you consider cosmology, is really contracting and expanding. And so I can have this universe which is shrinking on one side, the green universe, going through everything in reverse order. And then it goes through this quantum region, the Big Bang, and it comes out the other side as the universe we see. So what I want to end by telling you is that I can't show you the equations. Of course, this picture stands or falls on the mathematics and the equations, which I can't really explain in a talk like this. So it's purely pictorial. But what we found, to our surprise, actually, is that when we developed this picture of a double-sided universe, it very naturally explained the dark matter. And that's not, we weren't expecting that. So I'm just going to tell you in a couple of minutes how it succeeded in doing that. In order to explain the dark matter, I have to tell you a little bit more about what we know about physics. So we know there are some particles. They're called quarks. These make up the atomic nuclei. There are also other particles called leptons. One of them is the electron, which orbits atomic nuclei to make atoms. These particles all couple to the Higgs boson, which gives them some of their mass. There are forces. There's a photon, the particle of light, and some other forces. And then we know that there are also some rather strange particles called right-handed neutrinos. And I won't really have time to explain what they are, but just to say that we've got very strong evidence that, that there are additional particles. And these turn out to be, one of them turns out to be the simplest known candidate for the dark matter. And of course, all of these particles and forces are combined together by gravity, which governs the whole universe. So let's focus on the right-handed neutrinos. And again, I'll just explain in pictures. The neutrinos we can see in the laboratory are left-handed. They're very light particles, as this picture indicates, this seesaw. And the best explanation for why these neutrinos are so light is that there are some heavy neutrinos, which are there in nature, but they're too heavy to make in the laboratory. It would take too big of an accelerator for us to be able to form them. But they exist in parallel with the left-handed ones. And there's a mixing between them, a tiny mixing between the left and the right-handed neutrinos. And it turns out that the heavier you make the right-handed neutrino, the lighter the left-handed neutrino is. This is called the seesaw mechanism in particle physics, and it's very successful. So it says that if there are these right-handed neutrinos around, it explains why these left-handed neutrinos are so light. So this is rather well-accepted physics, which I would say we more or less know is true. Before our work, nobody suspected these right-handed neutrinos could be the dark matter, at least not in this very simple way I've described. And so it turned out that this whole picture of a two-sided universe allowed us to calculate the abundance of right-handed neutrinos formed in going from one side of the universe to the other. So we could calculate that mathematically. We then say, if those right-handed neutrinos only couple to gravity, one of them only couples to gravity, and it turns out quite easy to enforce that mathematically, then we can precisely, then if we assume it is the dark matter, we can calculate its mass. So we have a very precise prediction that one of the right-handed neutrinos has exactly this mass, and then it's the dark matter. So that explains the dark matter, it couples only to gravity in a very economical model. Of course, we have to test this model. Fortunately, it makes one prediction, that the corresponding very light neutrino is exactly massless. And this, it turns out, will be tested over the next decade. So if you invite me to speak 10 years from now, and if this experiment has been performed, and if it confirms that the lightest left-handed neutrino is exactly massless, then you may have to invite me as a Nobel Prize winner, because that's surely what would be the result. So it's amazing, in fact, that the way in which we will detect the right-handed neutrino is by seeing how matter clumps on large scales in the universe. And this Euclid telescope, which will launch in 2 years' time, will be able to do that. So thank you for listening to me today. I hope at least I've given you some impression of the ambition and the wonder of this field. It's truly a privilege to work in this field and also to share some of our excitement with you. Thank you very much.